Welcome to the second talk today, which is by Sangmin Lee, and he's going to tell us about the classical iconelytics, from the Magnus expansion. So, thank you.
Thank you. Yeah, let me thank the organizers for inviting me, and thank you all for coming. I'm giving 2 lectures, and I'm trying to make both of them accessible to students with very little background. So the first topic is classical iconal, and the broad context covering both this one and tomorrow's lecture is to use amplitude techniques for gravitational binary. And I'm sure many of you heard something about this topic. It's been very active. So in a sense, we are computing the GR correction to Kepler problem, which is a standard material in any GR course. But the textbooks usually cover only the leading order correction, whereas the experts try to go much further. And using amplitude techniques like Feynman diagrams to do the GR computation dates back to old days, at least to 1970s, if not earlier. But the whole field gained a huge momentum around 2015. One obvious reason is, of course, the detection of gravitational wave. But around the same time, there's been, there was a lot of theoretical development that pushed the boundary very quickly, very far. So let me begin with a few basic jargon in this field. That is the distinction between the post-Newtonian and post-Minkowskian expansion. Post-Newtonian is mainly for bound orbit, where the virial theorem dictates that the potential term and the kinetic term should be around the same order throughout the motion. So when you do a perturbation theory in GM over R, you keep the same order terms in this velocity expansion. On the post-Minkowskian side, you don't assume, well, it's more for a scattering orbit. And since the orbit is unbounded, there's no restriction on the magnitude of the velocity. So you usually keep this GM over R as your perturbative parameter, but you don't assume that the velocity is necessarily small, and you aim for an expression that is exact in velocity. No approximation in that regard. And I'm going to focus on the post-Minkowskian side and not saying much about the post-Newtonian side. The reason being that the post-Minkowskian one is more directly related to the amplitudes. So one thing we do in the post-Minkowskian business is to compute the effective Hamiltonian, which you obtain by, roughly speaking, integrating out the interchange of gravitons. So the 0th order is the free part, and all the interaction terms have this GM over R as your perturbative parameter. So the 0th order term is nothing but the special relativity expression for the kinetic energy. And the interaction terms as this form. And one important point is that these coefficients can depend not only on the position, but also on the momenta. Let me say it this way, yeah. For those of you who haven't seen the explicit computations of these PM Hamiltonian, let me just quickly cite the well-known 1 PM result. In the center of a momentum frame for simplicity, where this gamma is the relative rapidity between the two particles. So even in the leading order in G Newton, it's very nice. It's a very nice fact that you can actually find an exact expression in velocity. There is another expansion that you can do within the post-Minkowskian expansion, and the effective, the counting parameter is the mass ratio. So for the leading order PM Hamiltonian, we managed to write everything as a single term, but if you look up the papers on the serious PM computation, you obviously notice that you get more and more terms as you go to higher orders. And one way to organize the terms is in terms of the mass dependence. We have two massive bodies with mass M1 and M2. I'm more interested in the relative mass ratio between different terms. The overall normalization, it doesn't concern us too much. So we can arrange everything in this pyramid-like way. So at 2 PM, we have two types of terms. At 3 PM, we have three types of terms, and so on and so forth. And what's sitting at the boundary of this arrangement is easily recognized as the probe limit. So, yes. Mm-hmm. People seem to like the term post-Lorentzian in the electromagnetic case. Yeah, so, and I suppose you want something like R, Q1, Q2 over R in this place, and this is the same. Yeah, so on this boundary area, we have this source probe approximation. So when we are in the point particle picture, where the position and momenta are the only variables, and you don't think about other degrees of freedom, then we are really solving the motion of a probe particle in the fixed background of Schwarzschild metric. And here, you can essentially solve the problem to all orders. In that regard, something non-trivial begins to enter at 3 PM, where you I mean, there is a term that you cannot compute from this pool picture. And something more serious appears at 5 p.m., where you get m1 to the cube, m2 to the cube, which is like 2 steps away from this source probe picture. So the leading experts in this field, in the non-spinning case, I think finished the computation of the 4 p.m. effective Hamiltonian all the way. And they pushed the 5 p.m. frontier a little further. And they did compute this source probe part and the first step away from this line. But I think this part is still an open problem that some people may be trying to solve in the near future. As a side remark, there are people trying to use this mass ratio and turn it into a systematic expansion scheme. So you basically do an effective field theory in this mass ratio, and you start from this probe limit where essentially the solution is known, and try to use the information to go deeper and deeper in this direction. And yeah, some of those approaches are called self-force program. So in a loose sense, this boundary case is the 0SF part of the whole scheme, and you can call this 1SF, and this is 2SF, and so on. So another basic fact to recall is that when we use tools like Feynman diagram, at 1 p.m. we have 2 massive particles exchanging a single graviton. At 2 p.m. we have exchange of 2 gravitons. And already at 2 p.m. there are quite a few diagrams. One small fact that puzzles a beginner in this field is that sometimes there can be classical contribution coming from loop diagrams. So, standard textbook claim is that the loop order is proportional to the h-bar counting. So loops mean quantum correction. That counting is not that simple if you have massive particles and massless particles in the same theory. So, but anyway, there are ways to systematically extract the classical contributions, and it is true that some loop diagrams produce classical contributions. Now, speaking of massive particles in classical mechanics, some computational schemes really start from the full-fledged QFT, where the spinless particles are described by Klein-Gordon fields. And they compute scattering amplitudes, and they use some systematics to integrate out the graviton exchange. And then eventually they land on this effective Hamiltonian. But one question is, do you really need all that? I mean, we are doing classical physics. We're not interested in quantum corrections. Well, classically, fields are fields, but particles are particles. So can we go back to more classical picture of describing everything and obtain the same goal in a more computationally efficient way? And So some people proposed worldline models where they actually treat these massive particles as particles, relativistic particle navigating in gravitational background. There are several slightly different worldline models, and my personal favorite is the so-called double worldline quantum field theory proposed by Mogul, Plevka, and Steinhoff in around 5 years ago, 4 or 5 years ago. And I'll say more about this. The other thing is, I explained the notion of post-Minkowskian expansion in terms of this effective Hamiltonian, but some people don't like the Hamiltonian too much. And one feature of the Hamiltonian that is not too great is the fact that the Hamiltonian has a mild dependence on the coordinate choice. So we are describing the dynamics governed by general relativity in the template set by special relativity. So the graviton exchange is mediated by the curved space-time, but the Hamiltonian itself is written on flat space. But when you project this curved space down to a flat space, there is some choice of coordinate system, and that's usually called the coordinate gauge choice. So in practical terms, different people may use different coordinate system, and of course they should describe the same physics. So you should be able to write down some matrix relation like this. And of course, the zeroth order is an identity matrix. And then the subleading corrections should come with, again, expansion in GM over R. Moreover, since we are working in Hamiltonian, we want this whole coordinate transformation be canonical transformation, so that the Poisson bracket works in the same way in both coordinate choices. If you don't like the idea of treating the Hamiltonian as your final product, there is a better alternative. You can focus on the observables, which shouldn't depend on this ambiguity in your choice of coordinates. So what are the gauge-independent observables in a scattering problem? Well, it depends on how many degrees of freedom you have in your dynamical system. But of course, in a scattering process, one of the most obvious one is the deflection of your momentum. So you compute the incoming momentum, outgoing momentum, take the difference. And this thing shouldn't depend on your coordinate change, because asymptotically, everything is the same. And the main topic of this lecture, the classical iconal, came about while we were thinking about the ways to compute the observables. When it comes to the methods of extracting observables from amplitudes, one of the most well-known process is devised by Kusawa, Maybe, and O'Connell, and it's usually called KMOC formula, which came out in late 2018. And the basic idea is extremely simple. You compute the observables in quantum mechanics and take the classical limit. And since we are in the amplitude community, we want to describe everything in terms of the S matrix. And before we start taking the classical limit, let's use unitarity to turn the S matrix into something Hermitian. So if S is unitary, this chi should be Hermitian, well, at least formally. Well, in general, in quantum field theory, this statement should come with a lot of caveats because the analytic structure of the S matrix is extremely complicated. But for our purposes, extracting some classical information out of this amplitude, we assume that all those analytic structure, the complications from analyticity will not matter. And we just take this literally. Well, there is a slight chance that we may fail, but let's just assume it and see what we get. So, and this incoming states should be carefully prepared to, mimic classical mechanics in quantum mechanics. But let's not worry too much about this state. Let's just focus on the difference between the operator at the incoming side, on the incoming side, and on the outgoing side. Then the outgoing operator is the conjugation of the original operator. Now I put I in the denominator inside the exponential. And from the undergraduate quantum mechanics course, you recall this expanded form of this conjugation. With n factorial as your coefficient. Now, we really want a classical limit. And if you look at this line carefully, you immediately notice that the number of commutators and the power of IH bar matches perfectly. And through Dirac's correspondence between commutator and Poisson bracket, you immediately jump to the conclusion that there should be an analogous statement in classical mechanics where everything is written in terms of Poisson bracket. dot. And sometimes to simplify the writing, we introduce this exponential conjugation. So I just argued for the existence of a function in classical mechanics with motivation coming from quantum mechanics. I said absolutely nothing about how to compute this function, but I'll come back to it soon. Well, in most cases, we will rely on some perturbation theory to compute this function. So in a situation when we can expand this function chi as a power series in some coupling constant, then we can also write this relation between O prime and O in a perturbative way. So the leading order difference is dictated by the leading order term incoming phase space to outgoing phase space. And both the incoming and outgoing phase space are supposed to be free phase space. So the interaction is living in the bulk, and that information on the interaction is encoded in this chi, but the space itself, the incoming phase space, the outgoing phase space, are for free particles. So it's literally the classical avatar of S matrix in quantum mechanics, except that we are staying away from all those subtleties associated with poles and cuts of this S matrix. Now let me move on to more computational aspect of the story. So, yeah. How do you compute these chi1, chi2, the perturbative classical iconal order by order? In the context of PM expansion, I explained that the probe limit is much easier. And As it turns out, the classical iconal agrees with the better known radial action verbatim. I mean, they are just the same, except that you have a slight different perspective on what are the independent variables. But as functions, they are literally the same. But the reason I'm introducing this general notion of classical iconal is that you know, the whole discussion is valid even when you are away from the probe limit, and also even when you throw in extra degrees of freedom. I mean, the discussion on that side was fully general. Yeah, going to the computational side of the story. To give some idea without going, without worrying too much about other complications, let me explain the methods in Newtonian mechanics. So you have a single particle in 3 dimensions under the influence of a potential. Let's say the potential is falling off fairly quickly, so that you know, the scattering problem is well defined. So how do you compute that classical iconal in this context? Well, in our paper, we explained 3 different methods. Well, they are all related, but roughly we divided the paper into 3 parts. The first one is solving the equation of motion, and then extracting the iconal from the solution. The second one is the magnetic expansion, which was part of the title of the paper. And the third one was some math called Hopf algebra. I'll give you some details on the equation of motion and magnetic expansion, and just briefly mention some aspects of Hopf algebra. Well, we know the equation of motion. And for a generic potential, we don't know how to solve the equation of motion exactly. But there is nothing that stops us from solving it, you know, perturbatively, order by order. So without the potential, the trajectory will be a straight line. So we put in the straight line from the beginning, and then look for the deviation from the straight line, which we call delta x. And then the momentum should go like mass times v plus mass times the time derivative of this delta x. By perturbation, I mean this delta xt can be arranged as the first order, second order, third order, and so on. Yeah, so let's try to solve this exercise at low orders. At the first order, you can almost solve it by inspection. You don't even have to write down anything. But yeah, let me write down just one single line. That is, to compute the change of momentum, you just integrate the force over your reference line. But since to obtain the first order momentum change, you only need the 0th order trajectory and just do the integration. And this should be the same as chi1 Poisson bracket with P. So from this relation, you immediately rid off the first order iconal this way. And in a sense, this is a classic result. You can find it or something equivalent in many textbooks, including the classical mechanics textbook by Landau and Lifshitz. But of course, from the second order on, things are not that simple. So you need a bit of algebra. So suppose you computed the second order impulse and recall the general relation where this second order impulse should be chi2 Poisson bracket with P and some extra term, which we can write this way. So you compute this, and you already knew these two things. So using this relation, by solving this relation, you can try to extract this chi2. Let me skip the intermediate steps and just present the result, which shouldn't look too surprising to any of you. And this R12 is the retarded green function as a function of T1 minus T2. Retarded green function. So it's 0 for t less than 0 and proportional to t or positive t. Yeah, so you can keep doing this to the third order, fourth order, and so on. But the computation time grows quite quickly. I think it's like factorial squared. So it kind of flows up. So you get tired soon. And the other thing is, there is something fundamentally wrong about it. The computations are fine, but what's the point? We define this chi such that it can generate all possible observables. It can encode all possible observables. But we are doing it in the opposite direction. We are computing the observable first and then extracting this chi. It sounds like a total waste of your effort. So is there a shortcut to computing this chi than solving the equation of motion? Well, the answer is, of course, yes, and the magnetic expansion plays a crucial role. But to set the stage, let me introduce some graphical notation. And rephrase the equation of motion computation using the graphical notation. So chi1 is represented by a big dot. And the first order impulse is represented by a star. These notations are invented by Jung-Woo Kim, one of my collaborators. And the propagator. And this arrow is to emphasize the fact that we have a definite causality prescription. So the computation leading to this second order iconal can be described graphically as follows. So the second order impulse itself can be written as star connected to a dot with an arrow, with a retarded propagator. And the term to be subtracted involves a Poisson bracket. And Poisson bracket produces two terms with a minus sign, which sounds natural because it's antisymmetric. So two similar terms with the opposite direction of the arrow and a relative minus sign. Then the combination, which is directly relevant to the second order iconal, is the difference between the two. Turns out to be after a partial subtraction, partial cancellation, we obtain an expression with two terms and a relative plus sign. And this is just right for extracting the iconal through a Poisson bracket. Poisson bracket. So roughly speaking, this P acts on these two vertices one at a time through the Leibniz rule. And this is the graphical notation for this whole integral here. And yeah, in the paper, we push this graphical computation to the third order. So you have many more terms, a lot more partial subtractions, and so on and so forth. So, sure. Why do you expect
divergence in time, right? If we go to the higher order, second order in coupling in 4 dimensions. So
sorry, why do you expect any divergence at all?
Because the trajectory with a Coulombic, if you have Coulombic interaction, trajectory has a logarithmic divergence, right? So
sure, the Coulomb potential has a slight divergence, the logarithmic divergence. But let's just assume that V is falling faster than 1/r.
Okay. So this doesn't strictly apply to 1/r potential.
I'm not assuming 1/r. I'm not even assuming central potential.
I see. No, but if I wanted to look at 1/r potential, then
yeah, if you're mainly interested in Coulomb potential, you can start with 1/r to the 1 plus epsilon, and then take epsilon to the 0 limit in the end. That's how usually you tame the logarithmic divergence.
So sorry, and just one small question. So
sure.
Can I also think of chi as an on-shell action where I specify initial and final momenta and just compute on-shell action in perturbation?
That's a great question that I was going to mention around the end of the talk. I keep hearing this statement, this chi is some version of on-shell action. But I still don't know what exactly the prescription is. I tried a few things, none of them worked. Maybe I just missed some simple point. So if you can help me, that'll be great. Okay, so moving on to the next stage. Of course, we were not the first people to imagine these things in a graphical notation. You know, the WQFT paper that I cited earlier, let me call it a formal WQFT. So in this 2020 paper by Mogul, Plewka, and Steinhoff, they mentioned a very intriguing statement. So they set up their theory in a quantum mechanical way. So you can do some path integral. Let's say you compute some sort of partition function there. Well, forget about all the loop diagrams. You just collect all the connected tree diagrams. And you can argue that that gives you your classical object. And they claim that your iconal should be the log of the partition function. And it sounds very natural. So when I first studied their paper, I tried to learn this relation. I mean, get some intuition, and eventually use the technique to do some computations. But after a while, we realized that this prescription requires some refinement, which we didn't know at the time. So suppose we just take this prescription naively and do some Feynman diagrammatics. So what do we get? Chi2 in this picture is simply this Feynman diagram. Yeah, sorry for this extra minus signs here and there. That's a matter of convention. The fourth order, we begin to see some more interesting diagrams. So if you ignore the signs, these coefficients are precisely the Feynman symmetry factor. So it's literally the textbook material. But what are these propagators? Should we use retarded, advanced, time symmetric? Which one? Well, up to the second order, it's not clear even after you finish all the computations because, yeah, up to the second order, the different prescriptions don't really make any difference, any real difference. But as soon as you reach the third order, you begin to see something interesting. So this chi3, which we computed using this well-defined equation of motion method, I mean, well, this method is not too efficient, but it works. The result is 1/3 of this guy plus 1/12 of this guy. And at the face value, this graph, I mean, this representation and this representation doesn't quite match. Well, there is some hint for the agreement. So things are kind of working together, but if you know this on 1/3, 1/12, 1/12, you can easily add them up to get 1/2. But if you are starting from this side, how do you know you split 1/2 into these three pieces? It's not entirely clear. So after finishing the third order computation, we knew what to do next. The next goal was to develop some systematics that can go to an arbitrarily high order and generalizing all these funny coefficients. And it's not too difficult to argue that, convince yourself that you want all possible tree diagrams. So to compute the nth order iconal, you collect all the tree diagrams with n vertices. And it's important that these trees are oriented trees. The orientation set by these retarded Green's functions. And this integral associated with the tree is the generalization of this integral for the 2-point. And that generalization is kind of obvious. You just look at the tree, you write down the integral expression. And this sigma of tau appearing in the denominator is the symmetry factor with orientation included. So the real unknown is this coefficient appearing in the numerator. So if we can find a way to compute this omega tau without too much difficulty, then we are done. And that's exactly where the Magnus expansion comes in. So yeah, let me move on to the Magnus expansion. It was proposed by a mathematician called Magnus in 1954. And the legend has it that he was inspired by an earlier paper by Feynman. Anyway, the setup is a familiar one for any physicist. So let's suppose we solve a time-dependent differential equation, ordinary differential equation, where this y is the unknown, a is the definition of the differential equation. So roughly speaking, this a is like a matrix, and this unknown y is a vector. Well, it doesn't have to be a matrix. As long as it can be regarded as an element of a Lie algebra, then the same formulation goes. And with the initial condition for the first order differential equation, we know that the solution exists. And the whole point of Magnus expansion is to express the solution as some sort of exponential. So for high energy theorists, this is like the time-ordered exponential integral of a sort. But yeah, he wanted to do this in a systematic way. Well, colloquially, you can also say that this Magnus expansion is a continuum version of this Baker-Campbell-Hausdorff formula. Because, the A's at different times don't commute, but nevertheless, you can package everything in this exponential. So one of the things that Magnus showed in his paper is that this omega, which is the final goal of Magnus expansion, doesn't depend on the initial condition, right? So you should be able to write down the differential equation for this omega itself. And yes, such a thing exists. And of course, the leading order is easy. It's just a of t, but it receives a whole lot of corrections. adjoint action where adjoint of x acting on y is simply x comma y in the usual Lie algebra. So this equation is exact, but in most cases you cannot solve it exactly. So you rely on a perturbation again. And so you introduce a formal power counting parameter. And you work order by order in that parameter. So the recursion formula for the nth order term in the expansion is a differential equation for omega n t as some nested commutator of lower order omegas. Where these coefficients is each positive and sum up to n minus 1. Well, even if you don't have a deep understanding of how this magnetic expansion works, you can use it without worrying too much about it. So going back to our original motivation, computing this classical iconal order by order, you can turn this recursion relation into an expression. I mean, the integral expression. So let me write the first few terms. And the Poisson bracket is doing the job for the Lie algebra in a more broad context. You know, if you search for magnetic expansion on internet, you land on a page where they have an explicit expression up to the fourth order, and they stop there. And the reason is that you know, the number of terms increased quite quickly after that. Anyway, you know, up to the fourth order, you can literally compute these Poisson brackets and reorganize the results in terms of these three integrals, and then, you know, compute these omega coefficients along the way. That's a kind of fun exercise. And this method of using the magnetic expansion without any further process is still more efficient than the equation of motion because there are less steps involved in the computation. But it's not much faster either. So we kept wondering whether there will be even faster ways. And then we ran into these papers by some mathematicians. And yeah, we learned that some mathematicians did a lot of work on magnetic expansion. And found some interesting math structure behind it. So there is this Hopf algebra by people called Galak, Ebrimi, Ford, Mongshong. Around 2010. By the way, this is not the same Hopf algebra by the Ghon and Kramer that came out earlier. It's like 1998 or something. Yeah, I don't think I have time to go deeply into this Hopf algebra, but I mean, our understanding of that Hopf algebra is somewhat shallow. But we can say for sure that this is extremely useful for practical purposes. So we learned enough of this Hopf algebra to cook up some interesting rules among these omega coefficients. I mean, some of them were known before us, but we found some extra rules. We combined the rules and turned the rules into an algorithm to compute these omega coefficients much more quickly. So at an early stage of this project, we were thinking that maybe the 8th order or 9th order will be our ceiling. So computationally, it's going to be too expensive, so we have to stop there. Now we have an improved algorithm, which compute the omega coefficients for all the diagrams up to n equals 12, which accounts for about 500,000 diagrams. And the algorithm runs for about half an hour on your good laptop computer. It's nice. Good. For the remaining 25 minutes, let me tell you some stories that's still under development. So, unpublished work. Yes.
So this tells you about omega, but it doesn't tell you about I, the integral. So
yeah, the integral is trivial. You just look at the tree, you know how to write down the integral.
Yeah, so I guess I was wondering if you could give us a sense of how hard it is to actually do the integral.
Doing the integral, that's a whole different story. And of course, it depends on your potential. Yeah, so for like Coulomb potential, it's not too difficult. We did some experiment with Gaussian potential, which was also kind of straightforward because Gaussian integral is always doable. But for a much more, very ugly looking non-symmetric potential, then no, it really depends on your model.
So like for the Coulomb potential, how many orders of, how many iterations can you do for I? In perturbation theory.
Well, we didn't push it too far because if it's literally the Coulomb potential with no extra ingredient, then we know that the classical iconon is the same as the radial action, and we know how to compute the radial action. So you don't really need this expansion in a sense. Yeah.
Can I ask a small question? So,
Sure.
Since you only use retarded propagator in your rules, are the radiation reaction effects, you have to include them by some extra rules if you go to higher orders, or are they somehow accounted for?
Right. So in the Newtonian example, you don't see any radiation.
Yeah.
So our current project is going back to the original setup where we have two particles in special relativity or general relativity interacting with either photon exchange or graviton exchange. There, of course, you have to include radiation. And yeah, since you asked anyway, one of my collaborators, Jung-Woo Kim, wrote a paper that came out last month, which showed some example in the gravitational case where both the radiation reaction term in the conservative sector and the radiation loss term in the really radiativity sector, I mean, all those things can be described in terms of this classical iconal, with the understanding that the classical iconal now should include the outgoing graviton or photon.
Okay, thank you.
Yeah, so this framework itself is very general and very universal. Well, so yeah, I'm going to tell you a little bit about going back to relativity and say what extra steps we have to do to make everything work. So suppose we consider a relativistic particle in electromagnetic background. And we prefer using first order action. Good. Yeah, there are two things we can do. Well, there are many things we can do, but one thing that is obvious is to extract the vertex vectors of the formal WQFT. I mean, we had no objection to the vertex vectors of formal WQFT. We had only some concerns about the causality prescription of the propagators. So let's assume that it's safe to extract the vertex vectors just by expanding this interaction term in the Lagrangian. So with straight line path plus some deviation, and expand everything in powers of this delta x, and that will give you the vertex vectors. So the zeroth order one turns out to be V mu, A mu. The first order one comes with V mu, F mu nu, contracted with V nu and delta x mu, which we abbreviate as electric field multiplied by delta x. The nth order vertex actually has two different looking terms. One is the symmetrized derivative of this electric field. And the other, with non-trivial coefficients, comes with derivative of F itself and importantly, delta x dot is attached here. So when we contract these vertex vectors to form propagators, this delta x and this delta x dot will produce different propagators. Anyway, despite this slight complication of the vortex vectors, we had a form conjecture for the final answer from the beginning. That is, compared to the Newtonian case, we should replace the vertex vectors by these things. But as far as the causality prescription of the propagators is concerned, there's no real difference between the Newtonian case and the relativistic case. We just use the same rule, and that's it. And we managed to prove the claim. There was a slight technicality. That is, you know, there is this well-known map between Lie algebra of vector field and the Poisson bracket of scalar functions in you know, Hamiltonian mechanics. So in the Newtonian case, although these two computations are equivalent, in practice it was simpler to work with scalar functions rather than, you know, commutators of vector fields. Here we don't have a scalar potential. I mean, this term is a mu dot times velocity in the Lagrangian setting, but you know, this x dot is not potential. So I mean, potential should be a function of x and p with no x dot included. But that was not a big deal since we were still able to use this picture with vector fields. So x of, I mean, the interacting vector field at any given time can be written in this way. And using, I mean, applying the magnetic expansion with Lie derivatives, I mean, Lie brackets of these vector fields go through and everything works. So it was a little tricky, but we didn't have any fundamental problem. What about the gravity background, which is, you know, our real destination? So again, we started from a very naive way of looking at the problem. So in the first order action takes this form, or if you insist, you can also work with the second order Lagrangian. And this kappa is the word line Einbein or Lagrange multiplier, whichever you prefer to call it. Yeah, so we want to compute the classical icono using this action. Working out the first few orders in the most naive approach is not too difficult. And we have some partial results. But we are stuck at a rather elementary point. That is, we are having a hard time producing a formula for the classical iconal, which is fully generally covariant. You know, here you can write G mu nu equals eta mu nu plus H mu nu. Or here you can write inverse G mu as inverse eta minus, let me write it H tilde mu nu to emphasize the fact that this H and this H tilde are not quite the same. But anyway, we just do some naive computations using this, either of these two pictures. We get some well-defined answer up to, say, the third order. But the building blocks are, the basic building blocks are linear either in H or H tilde. So if you're happy with the linearized expression for the connection coefficients or the Riemann curvature tensor, then everything is fine. But if you really want the nonlinear full general covariance, then we are not quite there yet. And it sounds like a very simple question, but we are spending a few weeks not going through that issue, so we are confused. anyway, we hope we can get out of this confusion sometime soon, and we should be able to report the result. I don't know, in a couple of months, maybe. Any questions so far? Okay, so let me finally land on the last page of my note. So what to do next? As I emphasized already many times, the notion of classical iconal is very general. So it works in any theory described by Hamiltonian, quite often with constraints. So one obvious thing to do is to add some degrees of freedom other than the most basic position and momentum. So one famous example is to add spin to your particle. But you don't have to restrict to spin. You can add some other degrees of freedom if you like. And my lecture tomorrow will say something about spins. And the second item was taken by a question from the gentleman, the radiation. So yeah, let me say it again. There are two things about radiation. One is the radiation reaction term that contributes to the conservative Hamiltonian. The other is the real radiation, where you observe outgoing photons or gravitons. Yeah. Even in these cases, the notion of classical iconal seems to be useful. And you know, Jung-Ho Kim had one paper last month. The other thing is, I briefly mentioned that there are some nice papers about self-force expansion. So the 0SF terms are the probe limit, where you can use the radial action to do a computation which is much simpler than what I explained today. And for 1SF or 2SF, or you know, maybe even more, some people are trying to use the lessons from the probe limit to, you know, improve the computation of 1SF and 2SF sectors. And our work is not directly related to this SF program, but we get some hints of overlapping. So for example, if we look at chi2 and chi3, I mean, our expression for chi2 and chi3, either in electromagnetism or in gravity, although our result is not final. In this paper by Cliff Chung and others that came out last year, they proposed something called the recoil operators, which systematically accounts for the back reaction of, I mean, the recoil of a heavy particle away from the fixed trajectory. So they pushed their result up to the 2SF order. Somehow, there is a strong similarity between this side and that side you cannot miss if you just look at the answers. For now, we don't have a deep understanding of why these agreements happen, but I'm sure we are pretty sure it's not just a sheer coincidence, and there is deeper reason for it. And so maybe if we can understand this relation better and use it for, you know, further improvements, then we may be able to recover the self-force program, you know, sort of a bottom-up approach where we didn't really include any self-interaction in our computation. Okay, that's all for today, and thank you for listening.
So I think we have plenty of time for questions.
Yeah, thank you very much for a very clear lecture. You said you weren't going to go into the Hopf algebra, but could you maybe just remind of the names of, you had the initials, and maybe
yes,
can you say just one or two sentences about to get some idea?
Yeah, the names are. So these are the three authors. And there is another paper by another mathematician called Murua. I don't know how to summarize things in a few sentences, but let me say it this way. When I was, reading these math papers, I learned that using these graphical methods for solving differential equations go back even earlier. For example, Cayley was known to have some tree diagrams in his papers in the mid-19th century. So yeah, one thing is these authors, well, actually all of them, focus on these rooted trees. So in our causality terminology, rooted means that there is one single vertex that has the largest time, and the causal ordering is perfectly well defined. I mean, it's a partial ordering, but there is no going backward. But in our setup, we have to consider both of these diagrams, or even some things like zigzag diagram at the fourth order. So yeah, in this sense of rooted tree, this is a non-rooted tree because we have two vertices competing for the largest time. So one thing we did is to generalize the known Hopf algebra structure to include non-rooted trees. I'm not entirely sure how the mathematicians started all this huge business of rooted trees. But there are quite a few papers, and the later papers are becoming more abstract, so harder to understand. But papers up to like 2010 are quite readable. So we were able to learn bits and pieces and turn them into some interesting formulas. Yeah, so sorry, I don't have a very good intuition about it.
Thank you very much. That's very useful.
About the gravity, as you said, there was some subtlety with the once you go to second order. Is it because of the three graviton vortex, or is it some?
We are not even interested. I mean, we are not even starting to incorporate gravity. I mean, propagating gravitons. Yeah, we are working in a fixed gravity background and just focusing on the single particle. Of course, eventually we want two particles and the two interacting with exchanging gravitons. But we are doing a sort of a warm-up exercise. And even here, general covariance is, I mean, of course, just the Lagrangian or Hamiltonian, they are all generally covariant. So the covariance is there. It's just that we are doing perturbation theory in a somewhat stupid way, so that the covariance is not 100% manifest. So we want to improve. Yeah, we just need to improve upon it.
Thank you. But that may necessitate need to have higher graviton vortices. I mean, just from Lagrangian perspective, to have gauge invariance, we will need all contact terms, right? Is that correlated with this issue, or is it just independent? So in general, if I just take a gravity action, then I would have to add all the higher order interaction to preserve gauge invariance. If I do perturbation theory, is this lack of covariance related to that, or is it just something else?
Well, maybe I'm missing something, but our assumption is that at this stage, we don't need to look at the graviton self-interaction, or I mean, the Einstein-Hilbert action.
Okay.
Doesn't matter.
Are there other questions? Okay, so if not, let's thank the speaker again and we break for lunch.